Alrighty, hi you guys. Today you're going to be learning about bonding and intermolecular forces of attraction. And spoiler alert, everybody, they're different. So just to clarify the difference. So there are things that are called intramolecular forces. And these are bonds that hold individual molecules together. So they are intra. They are in the actual molecule. These occur inside a molecule, like covalent or ionic bonds. Or there are intermolecular forces of attraction. And these are forces, not bonds, that attract many molecules to each other. So instead of looking at what is keeping a molecule together, like intramolecular forces, intermolecular forces are looking at what keeps different molecules attracted to each other. And so these occur between molecules, and we're actually going to learn about what these forces are. And remember, these are forces, not bonds. So what are some of the intermolecular forces? There are three different types. We have van der Waals forces, dipole-dipole forces, or hydrogen bonding. And these are attractions, again, between molecules. They are weaker than either ionic or covalent bonds, and they're responsible for determining whether a molecular compound is going to be a gas, a liquid, or a solid at any given temperature. And remember, I can't enforce this enough. These are not bonds, but forces of attraction. So let's talk about some of these bonds. So van der Waals forces are also known as London dispersion forces. These are the weakest of all the intermolecular forces, and they occur between all molecules and in all substances. So they are the weakest ones, but they are always there. So everything has van der Waals forces or London dispersion forces, no matter what. And they're caused by electrons moving more to one side of a molecule, which is closest to a neighboring molecule. The neighboring molecule's electrons are momentarily repelled away, causing a temporary attraction between the molecules due to a temporary dipole. So it's just about a shift of the electrons in a molecule to one side or another, which then causes a shift of the electrons in a nearby molecule away because of a repulsive force, which creates these temporary dipoles. And we've talked about what a dipole is. It's when a molecule has a positive end and a negative end. And that dipole, that temporary dipole, then creates an attraction between the positive end of one molecule and the negative end of another. And van der Waals forces increase the larger the molecule is. So here's my question to you. Which will have greater van der Waals forces, methane or ethane? Remembering that methane is CH4 and ethane is C2H6. Which one do you think it'll be? And my answer to you is it'll be ethane, because it has 2 carbons and 6 hydrogens, so it is a bigger molecule, therefore it will have larger van der Waals forces. The next up, we have dipole-dipole forces. These occur when polar molecules are attracted to one another. So these don't occur with temporary dipoles, these are actually polar molecules that are attracted to one another. The electrical attraction occurs between the oppositely charged dipoles of these polar molecules. The slightly negative region of a polar molecule is weakly attracted to the slightly positive region of another polar molecule. They're similar to, but much weaker than ionic bonds. And so this is kind of exactly what's happening in van der Waals, except for this isn't a temporary thing. It is a temporary dipole. It is a permanent dipole. Okay? And then finally we have hydrogen bonds, or hydrogen bonding. And again, I know it's called hydrogen bonding, but it isn't actually bonding, it's just a force. So it can actually occur in the same molecule or in a nearby molecule. So hydrogen bonding can occur in water, which would be between 2 water molecules, but it can also occur in DNA between different sections of the DNA, different molecules in DNA. It's actually, it is part of what attributes to the coiling of DNA. And I mean, don't check me on that because I'm not a biology major, but I'm pretty sure that it's one of the reasons that causes the coiling of DNA. The trick with hydrogen bonding is that it always involves hydrogen, nitrogen, oxygen, and fluorine or other halogens, okay? And you'll notice here it always involves hydrogen and nitrogen, oxygen, and fluorine or other halogens. So one way to think about this is that hydrogen bonding, I have had enough of this. NOF, nitrogen, oxygen, and fluorine. So the hydrogen is going to be bonded to the nitrogen, or the hydrogen to the oxygen, or the hydrogen to the fluorine. So that's one of the ways that I remember hydrogen bonding is I have had enough of this. A little fun thing for you guys. Water is a really good example. So what happens is that there's an attractive force between a hydrogen, which is covalently bonded to a very electronegative atom, and another electronegative element with an unshared pair of electrons. So let's look at water, because it's a really good example. So here you have a water molecule where you have oxygen and hydrogen, which are covalently bonded, and it creates, and oxygen is a very electronegative element that also happens to have 2 lone pair electrons. And so those lone pairs create a negative charge, or a negative dipole near the oxygen, wherein the hydrogen has a positive dipole. And so then the positive hydrogen is attracted to the negative oxygen. And so you get this attraction from hydrogen to oxygen of other molecules. And so again, this is a force of attraction, not actual bonds being formed. That's why you can see that they are dotted, not actual bonds. But they occur in water. It's really a great example of hydrogen bonding. Okay, so the strength of intermolecular forces varies depending on the type of the force involved. London dispersion, dipole-dipole, or hydrogen bonding. And the way that it increases is it goes from weakest to strongest. So London dispersion is the weakest, then dipole-dipole, then hydrogen bonding. Now my question to you is, how does the strength of the bond affect vapor pressure? Now vapor pressure is a property of gases, and what it is it's the pressure that a gas exerts on the liquid surrounding it. So most liquids and gases, or most gases exist in both a liquid and a gaseous phase, just depending on the temperature. And so when it is in a gaseous phase and a liquid phase, it's the amount of pressure that the gas is existing on that liquid phase. And so vapor pressure decreases with an increase in the molecular force, since with a weaker intermolecular force, substances can easily become gases, so they would have high vapor pressures, whereas with strong intermolecular forces, it's harder to go into the gaseous phase, so you're not going to have as much vapor or gas present, so you're not going to have as much vapor pressure. So vapor pressure decreases with an increase in molecular force. Or we can also look at boiling point. All compounds contain London dispersion forces, which we've already said get stronger the larger the compound is. So with that in mind, the bigger the compound, the stronger the force, the higher the boiling point. So substances that have stronger intermolecular forces, so hydrogen bonding, would have much higher boiling points than London dispersion. And bigger substances with London dispersion would have bigger boiling points. So you kind of look at the strength of the bond and then also look at the size of it in consistency with the van der Waals. So we're going to be doing a lab about intermolecular forces, and we're going to be looking at a bunch of different chemicals, and we're going to look at their boiling points, and so they're actually their evaporation temperatures. And so these are the following compounds that we're going to be looking at. Ethanol, which is CH3CH2OH, propanol, CH3CH2CH2OH, butanol, CH3CH2CH2CH2OH, N-pentane, CH3CH2CH2CH2CH3, and methanol, CH3OH. Oh, I'm sorry, and N-hexane, CH3CH2CH2CH2CH2CH2CH3. And so I want you to think about their intermolecular forces present and what that's going to do to their evaporation. So are they going to be able to go from the liquid to the gaseous phase, and what rank do you kind of think that they're going to go in? And so I want you to think about that for that lab. So think about intermolecular forces and what we've just learned when applying this to the lab. This is a direct application of what we've learned. And I will see you guys later.